Hello and welcome to Linear Algebra. Today I'm going to be talking about basis and orthogonality. To recap, let's talk about span. You will notice that almost everything has already been written for this lecture, and that is because I just gave this lecture to my computer that was not recording. So we may not have the benefit today of being able to see me draw things out, and that's simply because I don't have the time in order to go back and redraw things out for this. So I'm sorry about that, but this is the best I can do for you, and we may actually save time because everything's been written out already. Okay, let's recall span. Span is the space described by or that can be generated by some set of vectors. This can be denoted by span of vector vi through vp for some combination of vectors v1 through vp. So if we recall, if we had, say, two vectors, those together could be used to create a linear combination to form some other vector, or the set of vectors they could create would then be able to span, say, a plane. Then we also have whether or not vectors are independent. So if we have vectors that are independent, then the set of vectors there cannot be used to describe each other, in the sense of we cannot create vectors in that set from the other vectors in that set. So the definition here is an index set of vectors v1 through vp in Rn is said to be linearly independent if the vector equation x1 v1 plus x2 v2 on through xp vp is equal to 0 has only the trivial solution. So the trivial solution is what values for these x's could we use to create any of these other vectors. So we could rearrange this, is what this is saying. Like, let's say we subtracted out this one, put it over here. Could we use the other existing combination of vectors in order to create this one? And the answer is no, because these do not have the necessary components in order to make this one. And that's the whole point of independence, is trying to find vectors that are not already covered in the span of the vectors in our set, so that we can include more space covered by the set of vectors as we add additional ones in, or to ensure that the vectors that we have only cover cannot describe each other and therefore are not redundant. That is, another way to describe this is that the only way these vectors can cancel each other out is if they all have magnitude 0, which is to say that they don't have any length necessary to leave the origin. They're all just points at the origin, and that's the only way they can cancel each other out, is if they just essentially never existed in the first place. Okay. Moving on, let's cover basis. So this is what we're getting to today. A basis for a subspace H of Rn is a linearly independent set H that spans H. So a subspace is any subset of a space. So a plane in 3 dimensions would be a subspace of a 3-dimensional space. A line in 3 dimensions would be a subspace of a 3-dimensional space. A line in 2 dimensions is a subspace of a 3-dimensional space, or a 2-dimensional space. If you have a linearly independent set, those can be used to describe some span. That would be a way of describing a subspace. And the term we use for that is basis. So the basis is any set of vectors that that is independent and spans some subspace. Why is this different from just saying we have an independent set of vectors? the implication is slightly different, because a basis is keying into the idea that any vectors constructed from that set of vectors can be used as like a reference point for the vectors themselves. So that sounds all very abstract. If we had a map and we wanted to get from Dallas to New York, and let's assume that in this case that the world is flat and not spherical, and in this magical world we can only move north and east, or negative north and negative east. But in this case, we only need to move north and east to get from Dallas to New York. And we want to be able to find some combination of a certain amount of east and a certain amount of north in order to get there. Then we can refer to north and east as the basis for the vector that we will take in order to get to New York. However, just because north and east are the vectors that we're using in order to traverse this space does not mean that they are our initial reference point. We may be working in some other reference system, such as like, let's say we are working in our initial set of axes that we're working out of are like from the center of the galaxy out as a vector to somewhere on like the Oort cloud. That's like a place that exists beyond Pluto. So we have some line coming from the center of the galaxy outward, and then we have some other line that's perpendicular to that going up straight out of the plane of our solar system. That would form our XY coordinate plane. Like, so if we had the sun here and we had the Oort cloud going around like this, and we had all of our solar system kind of in these lines here, and we had some vector going like this, and we decided to use that as our main, like axis 1, x1 kind of thing, and we had a line coming up like this, which is going to be perpendicular to our x1, x2. Later we'll have a term for this perpendicularness, and it's going to be orthogonality, and it's going to be useful in dimensions beyond 2. So this is a two-dimensional example. Orthogonality is true for all dimensions, but it is a very useful term for us when we're working in 3, 4, 5, up to n dimensions. And let's say we have our planet, I don't know, here, and we're still working in like our north and east direction set, which might be like some little tiny vector like that, or maybe actually kind of like that if we assume that we're actually working on like a plane sort of thing, that we're actually on a planet, but in this imaginary sense our world is just a plane. And then we have like some amount of east going that way. You can see that these two vectors, these two little tiny vectors, let's zoom in, on this plane are going like that and like that. Well, those are not in alignment with these other vectors, but it doesn't matter because they are at right angles to each other, or they're otherwise independent. They don't have to be at right angles to each other to be useful to us as a basis, but they are not the standard basis, which is this axis. And so when we talk about basis, we're talking about using some set of vectors as our reference direction set, in a sense. And these don't have to be in alignment with the axes, the standard axes that your entire data are based off of. And so why do we not just refer to a basis as an independent set of vectors? It means because we're cluing into this other idea that we want to treat this as a frame of reference. Okay. Moving on from that, let's talk about standard basis vectors, which means that it would be useful for us to talk about the identity matrix. The identity matrix is something that we have only seen briefly before. It's this right here. And what this is this is the identity matrix for a 3x3, but this is a 3x3 identity matrix. This is useful for whenever you're multiplying something that has compatible dimensions, let's put it that way. So one of the sides, if you're multiplying this by another matrix, would have to be have a length of 3. So we'll get to matrix multiplication later. That will make sense later. But in essence, what this does is anything that you multiply by this, that you can multiply it by, will be returned to you. So if I multiplied the identity matrix by some other matrix, that other matrix would come out of that multiplication exactly the same as before. The identity matrix can be loosely thought of as in other kinds of algebra, whenever you multiply by 1, you just get the thing that you multiplied by it. The identity matrix is essentially the same, but for matrices, for linear algebra. So the columns of the identity matrix here, each of these is one of the standard basis vectors. So if we look at this first column here, we pull it out and we put it here. This is the first standard basis vector. This column right here is the second standard basis vector, and this column here is the third standard basis vector. For the generic case, we can see that we have a 1 for this first standard one, zeros, and then the rest are zeros all the way down to the end. So this could be arbitrary length. And then for the second one, it's 0, and then 1, and then all zeros. And then the last one is all zeros and then 1. Which is, if you look at here, it's the same format, just if you wanted to make this matrix bigger, and it's always a square matrix for the identity matrix, by the way. If you just pulled that corner right on out, you would just keep getting more ones going down. And each of those would be like standard basis vector 1, standard basis vector 2, standard basis vector 3, and so on, until you got to standard basis vector n. Okay, let's represent this geometrically. So if we want to see what these are, let's say, okay, we have our first axis here, second axis here, third axis here, and let's just ignore this for now, because previously when I was doing this lecture for the first time, I just reused this graphic for another example. So I'm sorry, it's not there. Let's just pretend. Okay. So if we want to draw this first standard basis vector, because it's of length 3, and which tells us we're able to work in 3-dimensional space, we would go, okay, well, the first element tells us that we are going to go length 1 in the first dimension. Okay, and then we have length 0, no components in any other dimension, so we're just here. The second one says, don't go any amount down length 1, or down the dimension 1. We're going to go length 1 down dimension 2, and there we go, and nothing else. And the same thing for standard basis vector 3. And there you go. That's what they are. They're just vectors that are of length 1 that and have magnitude 1, which we'll get into in a second, that fall on the axes of our space. Okay, but basis vectors, as I described before, don't have to fall on the axes like the standard frame of reference for some vector space. And we'll get to an example of that in a second. First, let's get to why this B is just floating on this graphic. So B can be described like any vector in the span or in the subspace described by a basis. Can be described by a linear combination of the vectors of the basis. So in this case, B is equal to alpha 1 A1 plus alpha 2 A2, so on into alpha 3 A, or so alpha n AN. In this case, it's alpha 3 A3, where A1 to AN are basis vectors and alpha 1 to alpha n are coefficients of expansion. So when we talk about having some vector being described by a basis, we call it an expansion of the basis. And let me move my notes over. Okay. And so that's what we've done here. And then more specifically, in this case, we can say, I just changed the naming convention to B. So our coefficients of expansion in this case are B1 on through Bn. And our basis vectors are now explicitly the standard basis vectors. It is convention to write standard basis vectors using this E notation. So whenever you see those, you know that you're working with standard basis vectors. Or you know that whoever was writing their thing chose their variable naming very poorly. Example 2. So as I was talking about earlier with being able to traverse from Dallas to New York using our coordinate system right up here, we can tell using our bases that of north and east, there's only one way to get to New York from Dallas using some combination of north and east. If we have, assuming that we're in a flat plane, we're not a sphere, we can't loop around the sphere and get there. Our vectors do not curve, they're linear. We could take north and east and say we go, these numbers are going to be wrong. We all know these numbers are going to be wrong. 3 kilometers north and 2 kilometers east of Dallas to get to New York. Or we could say, vice versa, let's go 2 kilometers east and then 3 kilometers north to get to New York. The order does not matter, but by convention, when we write a vector, we always write what is in reference to our first dimension on top and our second dimension on bottom. And I don't want to confuse you by saying that the global frame of reference, those dimensions are going to be the same for our basis. So like, just because we're working in north and east doesn't mean that when we write a vector that says go 3 north and 2 east, that we won't be accidentally talking about traversing in our initial frame of reference. Instead, what we would do is we would say, I'm going to scale the combination. So here, I am going to scale the combination of my basis vectors by a certain amount. So in this case, with north and east, what we would say is, I'm going to go 3 kilometers north. This is my vector north, plus 2 kilometers east. And north and east will have some direction in the solar system coordinate system. So let's say north is actually like relative to this grand celestial coordinate system is actually like 3, 6. And then east is actually like, oh gosh, I want these to be orthogonal, but they're not going to be orthogonal. They're not going to be perpendicular to each other because I'm making it up on the spot. Let's go 0.5. Is that accurate? Sure. And then scaled by 2 and scaled by 3 is going to be equal to the location of like New York. So as a single variable, that's a single variable. Let's pretend. Even though that's not how we write variables in math, and that's confusing. So maybe I should just call it theta. Theta now represents New York. Okay. There we go. So that's how we traverse spaces using bases and how they differ from the like normal coordinate system that we're used to thinking in. This will be important for when we get to matrix multiplication. However, that's going to be a later lecture. Okay, an example now. Let's just say we have A1 and A2 as basis vectors, where A1 is 1.2 and negative 2.6, and then A2 is negative 0.3, negative 3.7. And we're trying to find, in the span of these, where is B11? Well, if we want to get to B11 from the origin in our initial reference system, we have to traverse 0.651 A1, and then we have to traverse negative 0.7280 of A2, in order to get to 1, 1. If anyone has any questions on that, I know that that is a lot to take in. Any frustration or any little thing that just didn't sit right, come talk to me, and I will do my best to re-explain. Okay, I am working out of the book for this course, which is the book by Boyd, and the next thing he covers is independence / dimension inequality. I'm also working out of another book, like half the lecture is from the other book and half is from this one. But since this is part of your assigned reading, I want to make sure that when you look at this, you aren't lost in the proof that he gives. And I'm not going to go through the proof that he gives of this concept. Instead, I'm just going to describe to you a way of conceptualizing what he's getting at without trying to prove to you that it's true. I want you to understand the takeaways here. I don't want you to have memorized a proof that will not give you intuition or confidence for understanding theory later down the road. So the independence dimension inequality is, okay, so let's say that what we have, catch up with my notes, okay, is, let's say we have this matrix here. And let me move it over so you don't have all the other stuff sort of clouding your view. Okay. The first thing we see in this matrix here is something that looks a lot like the identity matrix. And that's on purpose. So what I want you to be able to see here is, given that we were just talking about, oh, they're on the screen, these basis vectors here, we can see here that this vector, vector 1, vector 2, vector 3, vector 4, vector 5, this first vector is the standard basis vector for dimension 1. And this is a standard basis vector for dimension 2. And this is a standard basis vector for dimension 3. And then we've got some others. And when I was doing this lecture last time, when it wasn't recording, I realized that this isn't necessarily the best way of representing this, because it's hard to see that these zero vectors here are vectors, And it's also hard to see that they are linear combinations. They are dependent vectors of this set. So down here I rewrote it, and I was like, okay, you have your basis vector 1, basis vector 2, basis vector 3, and then you have vector 4 and vector 5. And so if these vectors here already describe the entirety of the three-dimensional space that we're in, you can tell we're in a three-dimensional space because we have length 3 for our vector. So this first entry, of course, is in reference to how far we are. It's an address for how far we are along the first coordinate, the first dimension, the first axis. The second one is how far we are along the second axis, and the third one is how far we are along the fourth axis. And there is no fourth or third axis, and there's no fourth axis here. So we must be in a three-dimensional space. And the terminology for this is an n vector is a vector of length n. A 3 vector, or 3 vectors, are vectors of length 3, which is a little bit confusing because it sounds like we're saying that you have 3 vectors in a set. No, it's that we have vectors that are of length 3. And the number of vectors we have overall in our set is 5, because we have 1, 2, 3, 4, 5 of them. So when we look at this, we can immediately say, when we look at this matrix, that because it's length 3, we are working in a three-dimensional space. And in this three-dimensional space, we have 5 vectors, where each column is a vector. And we can say that because we can see this identity matrix structure here, we can say, okay, well, I know one of the vectors is going to be a unit basis, or a standard basis vector for the first dimension, standard basis vector for the second dimension, and standard basis vector for the third dimension. And that this means that since we have these standard basis vectors, we know that these on their own are independent. We know that these 3 perfectly describe the entirety of R3, or the third dimension, or three-dimensional space. And then we know that anything in excess of that, any additional vectors that have length 3, so they're in this three-dimensional space, must fall within the span of these, because these already perfectly describe everything in 3 dimensions. So it's easier to see with these because these look more like real vectors than the 0 vectors I have here. These must be a linear combination of these. So if we scaled these up and added them together, so like this one is very clearly, if we wanted to break it apart, this one is going to be 1 of these, 2 of these, and 3 of these. So I took 1 times basis vector 1, 2 times basis vector 2, and 3 times basis vector 3, added them all together, element-wise, of course, which is the standard way of doing it, we would get this. And then the same for 4, 5, and 6, we would have 4 of this one, 5 of this one, and 6 scaled by this one. Add that together, and you would get this vector right here. So these 2 are dependent. They're dependent vectors. These are basis vectors. And from this we can see that if we have a matrix that is shorter than it is wide, there's no way we can have more basis vectors than 3, because we don't have the length of the matrix in order to do it. So we wouldn't be able to put in 0, 0, 0, 1, because it's not long enough to do it. We wouldn't be able to build that 4th dimension and have another independent vector. And so because of that, these vectors must be dependent. And so this whole set has to be dependent, because if any single vector in a set of vectors is dependent, then the whole set is dependent. So if that is true, then we know any time that the length, this dimension of a matrix, this length of the column, is shorter than the width of the matrix, the width of the set of vectors, we know that this must be a dependent set, because this is the case where we would have the maximal number of basis vectors. However, and we can describe this as the length of each vector by m and the number of vectors by n. So we would have an m by n matrix in this case, where if m is less than n, then this set is dependent. If m is greater than or equal to n, then it's the possibility that this set of vectors is independent. Okay, and that's what he's trying to get at in the Boyd book in the section on independence / dimension inequality. And he goes through a big proof. Well, he goes through a proof, depending on what you're used to. It depends on whether or not you consider it to be big. This is what I want you to take away from it. Another thing you should note, and I don't want you to get mixed up on this, is just because I have written the vectors in this order, and I've written them where it's very clear to see that we have like this identity matrix kind of thing happening right there. In real life, out in the wild, when you come across a matrix, it's just going to be numbers. Like, you're not going to know which vectors are going to be most useful to have as a basis. You're not going to know which are independent. You're not going to know which are dependent just by looking at it. That requires further inspection. But what I do want you to know is anytime you look at a matrix that is short and fat versus tall and thin, I want you to be able to immediately look at that and be like, oh, okay, I know how many dimensions I'm working in, I know how many vectors I have, I know whether or not this could be have a set of independent vectors, I know whether or not these could be basis vectors. Those are the takeaways from this. No one that I have ever met is magical and can just look at a matrix and be like, my superior brain powers have told me that this is the set of basis vectors for this set of... That person might exist. I've never met them. Okay, anyway, moving on to orthogonal and orthonormal vectors. I ran out of space here. I don't want to fit in this little tiny spot, so I've moved to the next page. All right, so I hinted at this earlier about what orthogonal and orthonormal vectors are, but the way I'm going to approach it here is by not really explaining to you what they are for a little while. What you need to know for now is that they are orthogonal vectors are vectors that have some relationship to perpendicularity. They're independent vectors, and we'll be getting to that definition later. I'm not going to try to explain it to you before I've given you the proper setup. So for now, I'm going to take a step back and say, do you remember when we covered inner products or dot products or any of the cosine angle stuff that we talked about previously? Because that's what I want you to be thinking about right now. So first, I'm just going to give you a couple of vectors. And those are, right here, we have vector u, and that's composed of u1, u2 onto un, and a vector v, v1, v2 onto a vector vn, and this is going to, we are going to multiply them together, and what that is called, and how we're going to write that, is u transpose times v is the same thing as saying we're going to find the inner product, which is the same thing as saying we're going to find the dot product, and we can write this as u dot v. And the reason why this is in this nice special box is because you will see this everywhere, like everywhere. And if you don't recognize what this is immediately, then you're like, oh, I don't really remember anything called inner product or dot product or anything like that. I'll show you in a second. It'll look really familiar. But this stuff shows up in descriptions of like the math behind algorithms. This kind of stuff shows up all the time, and it's not necessarily in the terms of like vector multiplication that we have here, but we can do like the dot product between like two matrices or something, and I'll be like, oh, okay. But it's essentially the same thing that you're seeing here, but we'll talk about that more later. For now, just become familiar with the notation u transpose v and u dot v, because in time, if you pursue the math behind matrices, these will become your best friends. And so it's good to become very comfortable with what they mean. All right, so what does that mean? What is u transpose v? So we take, actually I should go back. Take u and transpose it. Again, I haven't really covered what transpose is very much. We're getting there. I swear, we're getting there. Okay, v, copy it on down, and then the inner product of them is finding this linear combination, which we've seen a ton. So first element times first element, second element times second element, and so on, all the way down. And all these add together, and they give us a, in this case, a scalar, because these are just individual, these are scalars. These are just single numbers. Okay, so let me give you an example just to refresh your mind of something a little concrete, rather than this abstract onto some seemingly indefinite n notation, though this is not written for infinity, per se. Very discrete kind of notation. Anyway, so we have u is equal to 2, negative 5, 1. V is equal to 3, 2, negative 3. Cool. We want to find the dot product of them, which is the same as u transpose v. So take u, transpose it, take v, copy it down, multiply them together, and what we get is first elements, second elements, and third elements together, multiplied together, and then the results of those added, and that is equal to negative 1. That is something we've seen a lot before, just maybe a slightly new terminology for it. Okay, cruising right along. What can we do algebraically with these? So let's let u, v, and w be vectors in Rn, so some space, and let c, in some real space, and let c be a scalar. Okay, then what we can do is do the dot product of u times v or v times u. That's pretty straightforward. If we reversed these two and made v the transposed one and u the not transposed one, the only thing that would change here is that these two numbers would be flipped. And since we know that when we multiply things together, it doesn't matter what order we add them in or multiply them in, the output of this little tiny function right here is going to be the same, and the same thing for here and the same thing for here. So when we add all these together, it's still going to equal -1. Okay, now let's look at u plus v times w. So this is just saying it does not matter if we essentially distribute in w or not. That is something we can do. C in this case is a scalar. So does it matter if we multiply the scalar by one of them, scalar by both of them, or the scalar by, the scalar of the product of them, or the scalar by the other vector? Does not matter, you can do it in any order. And then if we multiply a vector by itself, if we do the dot product of a vector by itself, it will always be greater than or equal to 0. So it can never be negative, just like when you square something, because that's essentially what this is. You are squaring a vector. You could never get a negative number. And the same thing is true here. And the only way you can get 0 is if u is 0 in the first place. So if you multiply 0 by 0, you get 0. If you multiply any number larger than 0, you're going to get a non-zero number. There you go. Or at least by itself, you know. Again, here we have the if and only if notation. So let me read this out completely. So u dot product u is greater than or equal to 0, and u dot product u is equal to 0 if and only if u is equal to 0. And we can write this if and only if as IFF. This is something you'll see in papers, in other mathematical writing, and people will just substitute it into like a paragraph. They'll just be like, blah, 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 thing can be true, IFF, if and only if something else. And they won't give you this explanation. So when you see IFF and you're like, what? Does that say if? It's if and only if. There you go. Okay, and so from these nice, neat algebraic properties, we can derive this. Sorry, it's not a derivation. We can construct this, and this may be handy to you in further math. So C1 times U1, so a scalar times a vector, an element of a vector, plus C2 times U2 onto CP times UP times a vector W is the same thing as the first scalar times the first element of vector times the vector itself plus the same format onto the last scalar times the last element of vector times the vector, some other vector. And that's just something that happens to be the case. So that might be useful to you. Okay, I'm going to slightly tangent again and remind us of what norms are. There's a lot of things to keep in mind for what we're going to. And a lot of things where I just like want you to remember because it might help your thinking for understanding this. Not that there's going to be like a direct logical connection between what I'm showing you and like what we're going to be talking about, but like I figure if I activate these networks in your mind, you might have an easier time reasoning through the next little bit. So here we go. Recall what a norm is. So a norm, this little dude right here, is the length of, or the magnitude of some vector. So the length or norm of V is the non-negative scalar, this dude, defined by the magnitude of V is equal to the square root of V dot V. So very close to V, that is V times itself, which is V squared essentially. But we don't write it that way. Which is equal to the square root of the elements of V squared and then added. So V1 squared plus V2 squared onto Vn squared. And then if we look at the magnitude of b squared, so if we square this dude, we get v times v. So that's essentially this whole section where you square both sides, and what you can do is, so you would square that guy, and then for this one, when you squared this side, you would remove the square root. And there you go. That's as a reminder of what magnitude is. That may come in handy here in a minute. Another thing I would just like to remind you of is of the buildup for the distance formula. So let's say that we have two vectors, a and b, and we add a and b together. Okay, so the distance of the vector that is a plus b is the hypotenuse. So let's say this is a right angle, and this is our angle right here. This is a, this is b, this is the hypotenuse. Then the length, or the magnitude, or the norm of the hypotenuse is given by the magnitude of a plus b squared, which is equal to a squared, magnitude of a squared plus the magnitude of b squared. Magnitude of a plus b is equal to the square root of a magnitude of a squared plus the magnitude of b squared. So we just took the square root of both sides, okay? And another thing to recall is that if we want to take the magnitude of just a single vector, so if we just wanted to take the magnitude of a itself, it would be, I'm just going to rename this as x. So magnitude of x is equal to the magnitude of x squared, square root of the magnitude of x squared, which is equal to the square root of x squared, because the formula for the magnitude is just there. And so if we looked at this, it's just the first element itself, and this is just going to come out to be equal to this. And then what this is, okay, so if we take the square root of something squared, all that is the absolute value of the thing itself, because let's say we took the number -2, squared it, which is 4, then we square rooted that, we would get back to 2, which is just the absolute value of the initial number. So there we go. Absolute value of x. So the magnitude of x is just the absolute value of x. And that will be handy to keep in mind. Then here, what we have is, you can see I made some mistakes the first time through. Okay, so let's say instead of having our vectors be coming from the origin, and instead this time we're trying to find the magnitude of the vector itself. And what we can think of this as is, we could break this up into two vectors. We could say that we have some amount on this axis, or this basis, and we're going to have the amount of x1 of it. So it's going to be scaled certain length by x1, and our second element is going to be scaled by some amount of x2. And then we could add those together, and that would give us this vector right here. So we can break that apart. So if, let's say this is our vector right here, and this vector is defined by x1 comma x2, that's our point right there. We could say what amount of x1 and what amount of x2 take us there. Okay, well, we know that. That's this vector right there. And so if we want to figure out the length of this, we can think about it as if this is its own vector, and this is its own vector. And then we're back in this territory, where we're like, okay, well, we have a certain amount of A, we have a certain amount of B, and then we want to find the length of the hypotenuse between the two. Okay, well, that's the distance from here to here. Okay, and that we know in the case of these two vectors being on a right angle, which we know because we're working with standard basis vectors and we're working with just the elements inside the vector itself, so this is just going to be the Pythagorean theorem. So a squared plus b squared is equal to c squared. C squared is the length of the hypotenuse, which is the distance. So a squared is x1 squared. The length of x2 is the absolute value, of course, because it could be negative, but x2 squared, and then square root of that is going to give us this. Cool. Let's keep that in mind. Wake up that part of our brains, and then I will move on right now to actually getting into what orthogonality is. Give me a second because I'm losing my voice. So, okay, cool. Moving on. Definition. Two vectors u and v are orthogonal together to each other if the dot product of them is equal to 0. So first let's recall perpendicularity. So perpendicularity is when we have these two lines and they are at a right angle to each other. Orthogonality is can be loosely thought of as the multidimensional case of perpendicularity. A set of orthogonal vectors is a set of vectors that are all orthogonal to each other. So each pair of vectors is orthogonal to each other. So each pair of vectors satisfies this constraint. And let me go into that on another piece of paper. Let's take a moment to recall the discussions we had previously about vectors and angles. Some dimension system like this. And you have some vectors in there that have some 90-degree angle, where this angle here, theta, is equal to 90. Okay, and then let's also recall the equality we had where we would have the dot product is equal to the magnitude of u times the magnitude of v times cosine theta. Now, when we had an angle equal to 90, this was equal to 0. Okay, so for when this was 90 degrees, this was equal to 0. What you can, if you want a fast and loose way of thinking about this, you can think about what this is telling us as saying that this is giving us information about how the two vectors u and v have scaled each other based on how much they're able to describe each other's direction. In this case, because they are orthogonal, they can't describe each other's direction at all and give us 0 as the result. Because of this, if we ever want to be able to tell if two vectors are orthogonal, we can calculate their dot product and see if the result is 0. So if we ever want to know if two vectors have a 90-degree angle between them, we can multiply them, find their dot product, and if it's 0, cool, we have two orthogonal angles. So let me write out this theorem for you. Okay, if S is equal to U1 on through UP is an orthogonal set of non-zero vectors. So a bunch of vectors, none of them are 0, and we know all of them are orthogonal, then S is linearly independent and is a basis for the subspace spanned by S. Okay, what does this mean? So we know bases are independent. Bases don't have to be orthogonal because you can have two vectors that describe a subspace that aren't perpendicular to each other. They can be you know, at a 30-degree angle to each other or something. And they can describe some subspace. And that subspace, we're going to say, is spanned by that set of vectors. And that set of vectors we're going to call S. And the name of each vector is U1 or U2, U3, whatever, onto UP. And that these exist in some real space Rn. And that's what this is getting at. Okay, so if we have a set of orthogonal vectors, we automatically know that A, the vectors in there are independent, and B, the vectors in there are a basis for the subspace of that set of vectors. There we go. Okay, let me give you another definition. An orthogonal basis for a subspace W of Rn is a basis for W that is also an orthogonal set. So what this means is that if we have an orthogonal basis for a subspace, so we know that all the vectors in there are orthogonal to each other, we know that they describe some subspace with their span, and they exist in some real space, Rn. What we know is that they are a basis for that space and that they are also orthogonal. It's just a very circular definition. Okay, so now I'm going to give some theorems and an example, and that is what we are going to end with today, but it is a longer example. So let me first give you a geometric description and then some theorems, and then we'll break down the geometric description. We can use a set of orthogonal basis vectors to describe any vectors in their span. Let me show you this geometrically. So let's say that we have an axis, and let's say we have another axis. And then let's say that what we have is a basis vector here. And this basis vector we're going to call U. This is going to be a normalized basis vector, which we'll get to what unit vectors are in a second. It just means that this has the length of 1 and is a basis vector. And this thing has a span here. Okay, so that line is its span. And then we have another vector that is orthogonal to it. So I'll do that as best I can, given just eyeballing it. And I'm going to draw that. Draw that here. All right, and I'm going to say that we have some vector z here. And this vector z is going to be a vector, just any vector, in the span of the vector that is orthogonal to u. This vector z, of course, is orthogonal to u, but this one I have not normalized. This one doesn't have length 1. It's just a vector. And then we have the vector that these two can create. And I'm going to draw this here. I'm going to say up to there. This is going to be y. the amount of y that is described by the vector u, this, if we scaled vector u, like maybe if we multiplied it by 2 or something, would be the amount of y that is described by the basis vector u. And we're going to make this its own vector. This is going to be the vector I don't like the naming convention used on this. I'm going to call this something else. I'm going to call this W. Yeah, that works. So it's going to be W, and then so this whole thing right here. This is W, which is the component of y described by a multiple of u. So some scaled version of u. And then we have z here, and I didn't do it quite right, but I was trying to make it so that this would be straight across. That's z. Let's pretend that right there is z. And this is this thing right here is z is the component of y described by z. So, and z is this this whole axis here. I mean, it's not. It's this vector here, but I don't want to have to name the vector that is orthogonal to u because I don't want to confuse you later. So you can just think of it as the part on this axis that is describing y. Okay. So let's say that z and u are, or, oh, I'm writing off the edge of the screen. Orthogonal basis vectors. Cool. Now I'm going to take a moment to talk about unit vectors because we just saw one, and it's important to know what we're working with. So let's go up here and have a moment to talk about basis vectors. I mean unit vectors. This is actually going to be about orthonormal. A unit vector is a vector with length or magnitude or norm of 1. So write that out. Okay, so the process of scaling a vector to have length 1 is called normalizing a vector. So we denote unit vectors as u. U is a unit vector. Okay. In order to find a unit vector for some vector v, we divide the vector by its magnitude. So if I want to find the unit vector for v, I say, okay, I have v. Here's its magnitude, right there. and that's going to give me a vector that has the same direction as v, but has length 1. And I can also rewrite this like this. Okay, so what are orthonormal vectors? Orthonormal vectors are a set of vectors that are orthogonal and normalized, so unit vectors. An orthonormal basis is a set of basis vectors composed of orthonormal vectors. Okay, so when we look at this over here, this right here is a normalized version of W. So if I wanted to find U from W, what I would do is I would say W divided by the magnitude of W is equal to U. In some cases, it might even be better to specify which unit vector you're talking about if you have multiple, in which case I could put a subscript on this. I could be like U subscript W. So it'd be like I'm talking about the unit vector in the direction of W. And so in this case, U is an orthonormal vector. Z is just orthogonal. So Z is orthogonal to U. U and V are a orthogonal set. U itself is orthonormal. If U and Z were both unit vectors, then I could say that they would be an orthonormal set of vectors. Let me give us one more thing. I'm not going to try to justify why this is true. I'm just going to give it to you so that we can do this example. And then we'll dive into the example proper. Okay, so theorem. So let's say we have the set of vectors u1 through up, and let's say that they are an orthogonal basis for a subspace W that exists in Rn. For each y in W, so for each vector, each point in W, the weights in the linear combination describing that vector, so y is equal to the linear combination of u1 through up given some weights. And the description, the definition for those weights is given by Cj is equal to y times uj over uj times uj. So, can't see it. There we go. So each of these u, each element here, or sorry, each vector here has its own weight, and that is given by this equation right here. Now for the problem itself. Okay, let's assume we have two orthogonal basis vectors and I'm going to call them W and Z, and these are going to be our orthogonal basis vectors. Okay, we want to be able to describe the vector y by a combination of W and Z. So we want to be able to say y is equal to some coefficient times W plus some coefficient times Z. And in this case, the way we're defining it is we want these to be entirely the components that we're talking about. So this would just be scaled by 1 in this case, which is to say we just want to be able to have two vectors that compose y. In this case, we have some definition for what we're looking for. So we have y is equal to y is equal to 7, 6, and u is equal to 4, 2. And we want to find the orthogonal projection of y onto u. Okay, what does that mean? So what that's asking is we want to find how much of u we need in order to build the u component for y. So we want to be able to say when we have our u component here, span u, and we have our y vector here, we want to be able to find this vector right here, which is our w vector. So when we say projection, that's the same thing as saying I want to know the shadow of y onto the span of u. Or another way of saying that is I want to know how much of u does it take to build the u element of v. So all these are just different ways of saying I want to find w. And when I add z to w, I can get y. And all this is another way of saying there's some linear combination out there of u and some other basis vector, which in this case we're going to say is the span of z right here. And between this component here of the shadow onto this span of z and the shadow onto the span of u, these two components together will build y. Okay, so let me repeat that. Find, let me write it down. Okay, find the orthogonal projection of y onto u, then write y as the sum of two orthogonal vectors, one in span u and the other one orthogonal to u, which is the same as saying span of z in this case. Okay, so we want to find, first step we want to do is we want to be able to find w. And the way we're going to find w is by using one of the theorems that I wrote down earlier that I didn't provide a justification for. And the way we can do that is we can say w is is a coefficient times u. And this coefficient same thing as a scalar, same thing as a weight, is we can express this as coefficient is equal to y times u over u times u. Okay, so this way we can just substitute this in, u times u, and then times u, because we have to bring this one down. Okay, well, do we have y and u? Yeah, we do. We have them right there. So let's bring them on down and figure out what this is. So y times u is equal to 7, 6 times 4, 2, and this is equal to 40. And u times u is equal to 4, 2 times 4, 2, and this is equal to 20. Okay, so now we can substitute that into here. So w is then going to be y times u over u times u times u is equal to 40 over 20 u, which is equal to 2 times 4, 2, which is equal to 8, 4. Cool, we have found w. That's neat. We have found the orthogonal projection of y onto u. That's neat. Okay. So we have found the amount of y that can be generated from u. Now, what we want to do is find the component of y that is orthogonal to u. So we want to find z. How do we find z? So what we can do is we can say that z is equal to y minus w. Because if we go right up here and we're like, okay, well, we just found w, we just found this whole projection-y part, and we're trying to find z. Well, what we can do is, since we know this, we could just rearrange this, and we can just go, okay, if we're trying to find z, let's solve for z, which is just y minus w, which is what we have right here. Okay, and looking through my notes, okay, so y minus w is equal to, well, we know what y is. Y is 7, 6, and we know what w is from right here, so that's 8, 4. Okay, and that together is -1, 2. Cool. We just found both of them, because this is equal to z. And then we can rewrite this. We can write this as, if we want to find y is equal to w plus z, make sure we have this all correct, which we should because this was fairly simple. We can say w, which is 8, 4, plus z, which is -1, 2, should be equal to y, which is, okay, 8 minus 1 is 7, 6. Okay, cool, we got y back. Neat. We were able to generate y from a combination of w and z. Ta-da! Now what we want to do is we want to know if these basis vectors, we want to make sure we did this right. So let's see if those two, let's just do it. Where should I do it? Let's do it right here. We want to know if, let's put W is equal to 8, 4, Y is equal to 7, 6, and Z is equal to -1, 2. We want to know if W and Z are orthogonal to each other. And we know how to check that because we know that they should be from here. Our whole point was that they should be orthogonal to each other and they should be basis vectors. So let's go here and let's say do our test for orthogonality, which is W times Z, or dot product Z, which is equal to 8, 4, dot 1, 2, which is equal to -8 plus 8, which is 0. They're orthogonal. Cool! Orthogonal. Check. And there we are. We were able to figure out a given one vector that we wanted to be a basis vector, and given another vector that we wanted to be able to describe using that basis vector, we were able to describe another orthogonal basis vector for it. And this is an example of how even when you have this initial frame of reference where you have the standard x1, x2 axes, and you want to be able to work in a different frame of reference using basis vectors, non-standard basis vectors, you can do that and be able to describe any vector in your existing space. And this will be useful later on, and that is all for now. If you have any questions, reach out to me on Discord, reach out to me any way you can find me. I will do my best to ameliorate any frustrations you may have, adjust the curriculum in the future, like whatever seems reasonable to me and whatever I can do for you realistically within my ability, I will do. So let me know. I'm here for you. I don't have significant bearing on your grade, and I am really just here to teach you. I want you to be able to be confident in this material. I want you to be able to go out in the world and use this as a tool in your toolkit to do whatever you want to do. So I want to make that happen. Thank you.